In this video, we're going to discuss the domain and the range of a relation. There's a lot of vocabulary here because we haven't talked really about the word domain or range. I've mentioned relation a little bit here and there, but haven't really talked about it explicitly. So first, let's start with a relation. A relation in math is a correspondence between two sets. So you could have sets of numbers, but a lot of times these numbers come from a real world context, such as people and their birthday. And then you can relate people to their birthday, and that makes a relation. Age and height can be related, and so in math we would call that a relation. And then the hours worked and pay received is another example. Sometimes it's just numbers, they don't have labels attached to them. So the last example I have here is an example of what's called a mapping. So here on this first one here, it's showing -2 is going to or maps to 1. 1 maps to 1 as well. 1 goes or maps to 2, and 0 maps to 2. And so even though it's arbitrary, just based on the way I drew the mapping diagram, this also shows a relation. It shows that 1 is related to 1 and 2, and so on. Alright, now that we see what a relation is, let's go on to the words domain and range. When you're dealing with a relation, the two sets of a relation are called the domain and the range. In the examples I gave before, the yellow would have been the domain and the green would have been the range. In general, the domain is where you start from and the range is what you go to. So if you think of a domain like a king's domain, that's his home base, and then the range of his rule is the extension of his home base. So notice that this has all of this has a cause and effect fill, or an input output. So we've talked about input and we've talked about output. Well, your domain is the set of all your input values, and the range is the set of all your output values. And in that way, it corresponds to x being the domain values and y being the range values. So again, their domain is the set of all the input values grouped together, and the range of a relation is the set of all of the output values grouped together. Alright, now that we have that down, let's look at, let's get into the meat of it, where we look at getting the domain and range, given a graph, determining the domain and range of the relation that's on the graph. For example, let's say we have this graph here, and I want to emphasize here what I'm doing. The graph basically is made up of these 3 points, and they're on the grid. And so we're asked to find the domain and the range of the graph. Now, basically the domain is all the x values that those points go to, so, or that are a part of those points. So here, this one has an x value of -2, this point has an x value of 1, and this point has an x value of 3. So what that means is that my domain is the set -2, 1, and 3. And notice here I'm using these curly braces. You use that to designate a set of distinct elements. So our domain is made up of the x values -2, 1, and 3. Now we'll look at the range. The range is all the y values that make up those ordered pairs. So if I go through my points here, this point here has a y value of -1, this point here has a y value of 1, and this point here has a y value of 2. So all of those y values together as a set gives me the range of this relation. In other words, my relation is the set -1, 1, and 2. So that's the domain and range for this graph, but this graph is a little peculiar because it's just made up of distinct points. Usually we have what we call in math continuous graphs that is connected all together. And so now let's look at finding the domain and range when it's a continuous graph. So here's a graph, and it's basically very similar to the previous graph, But this time, instead of 3 points that aren't connected, we have a continuous curve going between them. And it's important here to remember that a curve is actually made up of infinitely many points. So it's not any different than the points that are already bolded in. It's made up of infinitely many points that have all blended together, and every single one of those points has an x value and a y value. Now what that means is if there's infinitely many points there, there's infinitely many x values in the domain, and there's infinitely many y values in the range, and I can't list them all out. So we're going to have to resort to using interval notation, where we just say where the domain values begin and where they end, because we can't list them all out distinctly. Alright, so then to determine the domain, let's just start with the domain. We need to think about what x values all these infinitely many points map back to. Well, if I map all those points back, and there's infinitely many of them, basically they're going to fall somewhere in the range between -2 and 3. And so that means we can use the interval notation to describe them as the interval from -2 to 3. And that's reading off of the x-axis. You always read the domain off of the x-axis. And here I'm using square brackets because I have solid points here and here. This is starting to look like some sort of monster with a red beard. But regardless, that's how you do the domain. You read it back to the x-axis and you express the range of values there using interval notation. For the range, what we want to do, range is all the possible y values. So all those infinitely many points, we're going to think about how they come to the y-axis. So I do all those, but if I keep doing these ones on the other side, this set here will overlap. But then it'll keep going up and up. But they're kind of bounded between the values, the y values of 2 and the y value of 5. So all of those points, their y values are somewhere between 2 and 5. So the interval notation on that would be the interval from 2 to 5. Remember, when you're doing interval notation, you're always doing the smallest number first and then the biggest number. But that's what you do. For domain, you read back to the x-axis what the x value would be for all the points that are on the graph. And for the range, you read to the y-axis what all the y values would be for all the points that are on the graph. Let's do a few more examples. Alright, so example 3, find the domain and range of the relation shown in the graph. So here, this one's slightly different than the last one because we have an arrow, which means that this is going to just keep going on at the same tendency forever and ever. So that's how we'll read that arrow. Other than that, the process is basically the same. Let's consider what the domain might be first, and since you always want your values to go from least to greatest, I just start at the left side of my graph and then work across. So if my graph's made up of infinitely many ordered pairs, then all their x values are going to come back and I'm going to read them off of the x-axis. So it basically kind of ends up, in my head, I think about it in terms of the shadow the graph would cast on the x-axis. Now here, this is going to keep going, so there's going to keep being x values forever. So I can think of that as just, the tendency is it's just going to keep on going. In other words, my domain starts at the x value of -5, and then it's just going to keep on going forever into a positive infinity on the x-axis. At -5, I have a solid point, so I use a square bracket, and infinity always uses a parenthesis. So that's the domain. Now let's switch and consider what the range may be. Now for range, it's basically the same process, except instead of reading to the back to the x-axis, I'm reading to the y-axis. So I'm saying what would be the y value of this point? It would be a -3. But then the y value of this point, and this point, and this point, and this point, and all the infinite points there. Now then I go over and get these points, but these points share the same y value, so that doesn't pick up any new information for me for any of those points. But then these would go back here, and then up here keeps going back to the y-axis. Again, I kind of think of this as the shadow this graph would cast on the y-axis. If there was a sun over here, what would be the shadow on the y-axis? Or for this bottom part, what kind of, where would the sun not shine? So anyways, in this case, this works out to be a range from -3, that's this part down here, all the way up, and then up here it's not stopping. This is an arrow that's going to continue up forever, and so that's going to go to infinity. But now it's going to infinity on the y-axis. Those are y values going to infinity, and then square bracket and then parenthesis at infinity. Alright, let's look at another example. Alright, here we have another graph. This one is similar to the last one. The big difference here is we have an open circle on part of the graph instead of a solid dot. And these open circles work the same way they do when we were graphing linear inequalities, which basically means that the values will go right up to that point, but they don't include the point. For domain, we want to look at how the graph goes back to the x-axis, and so that's going to be starting here. This is an arrow, and so we're always going to read an arrow like it's going forever in that direction. So that's basically going to be for our domain pointing to -infinity. Then we'll continue to have x values all through here. Still got x values up here, and then this is an open circle. So that's at an x value of 5, but since it's an open circle, we'll use a parenthesis this time instead of the square bracket that we have been using. So that's the domain. That's all of the x values that are producing that graph. Alright, let's switch gears and look at the range now. For the range, we are seeing what y values each one of these points corresponds to. So here we have all these y values for this point. And we come up here, when we get to this guy, this is an open circle here. Okay? When I put the part of this graph back to the y-axis, it's just doubling up all the same y values we had already accounted for. It's important to remember that this continues on with this tendency. Okay? So if I continue that on, taking it back to the y-axis, what's going to end up happening is a point over here is going to give me a y value here and basically fill in that open circle I had before. And so my range is going to go all the way up through infinity, just plowing right over what I don't have on the right side is going to get filled in by what I do have on the left side. Now it's a one-eyed monster with a big red mouth. So my range will be -2 to infinity, because I'm starting down here at -2 and I'm going forever up. Go ahead and give some of these a try and see how you fare.